The second part of Isro-Vssc Technical Assistant Electronics and Communication Engineering previous year question paper with a detailed solution. The exam held on 2015. Advertisement number 284 and post number 1243. Up to question number 20 we discussed in the last video. Consider question number 21. Given figure shows a silicon transistor connected as a common emitter amplifier. The quiescent collector voltage of the circuit is approximately. Answer is option C, 14 volt. Here consider base voltage VB equal to Vcc into R2 by R1 plus R2. After solving, we get answer is 20 by 3. A quiescent base voltage VB is determined by the potential divider network formed by the two resistors R1 and R2 connected to the base of the transistor. And the power supply voltage Vcc as shown, with the current flowing through both the resistors. We know VB equal to 0.7 voltage. That is VB minus VE equal to 0.7 voltage. Substituting the equation 1 in 2. That is substituting the value of VB in VBE, we get VE equal to 5.99 volt. We know from the circuit VE equal to IE/RE. After rearranging IE equal to VE by RE, we get 0.5966 milliampere. Assuming IE approximately IC, the output voltage V0 equal to 20 minus IERC, 20 minus IERC, which is equal to 20 minus 0.5966, that is 0.6 into 10, that is 6 volt. 20 minus 6 volt equal to 14 volt. Question number 22. In a junction transistor, recombination of electrons and holes occurs in. Answer is option D, all the three regions. Consider the figure. The small amount of recombination occurs with the bases, holes and emitter electrons. The operation is the forward active bias mode of the operation is obtained by forward biasing the emitter base junction and reverse biasing the collector base junction. Electrons diffuse from the emitter into the base and holes diffuse from the base into the collector. Once the electrons arrives at the base collector depletion region, they are swept through the depletion layer due to electric field. These electrons contribute to the collector current. Two more currents include base recombination current and the base emitter depletion layer recombination current. The current due to recombination in the depletion region can be observed as an additional base current. The collector current do not include this additional current, since recombination in the depletion region does not affect the flow of electrons through the base. Question number 23. The maximum power dissipation capacity of a transistor is 50 milliwatt. If the collector emitter voltage is 10 volt, what is the safe collector current that can be allowed through the transistor? Answer is option A, 5 milliampere. The power capacity of a transistor is given by P dissipated maximum equal to VCE into IC, where VCE is the collector emitter voltage and IC is the collector current. Given that P dissipated maximum equal to 50 milliwatt, VCE equal to 10 volt. After rearranging the equation, we get IC max equal to P dissipated max divided by VCE max. We get the answer is 5 milliampere. To prevent the transistor from destroying or from excessive heating, the safe collector current would be 2.5 milliampere, which is less than the maximum allowed collector current of 5 milliampere. Question number 24. The transistor in the circuit shown in operating in. Answer is option A, cutoff region. Either forward or reverse biasing is done to the emitter and collector junction of the transistor. These biasing methods makes the transistor circuit work in four kind of regions, as that is active region, saturation region, cutoff region and the inverse active region. Consider the given transistor and applying the KVL, we get minus 5 plus IE into 5K plus 0.7 plus IB into 100K plus 5 equal to 0. We know IE equal to 1 plus beta IB. Put equation 2 in 1, we get 1 plus beta IB 5K plus IB into 100K equal to minus 0.7. That is IB is less than 0. The above equation implies that the base current is negative. That is opposite to the traditional PNP transistor. So the emitter junction is reverse biased. The collector voltage is 0 and this junction also reverse biased due to the grounding of the collector terminal. As both the junctions are reverse biased, the transistor is in the cutoff region. If the emitter junction is forward biased and the collector junction is forward biased, region of operation is saturation. If the emitter junction is forward biased and the collector junction is reverse biased, region of operation is active operation. If the emitter junction is reverse biased and the collector junction is forward biased, region of operation is inverse active. If the emitter junction is reverse biased and the collector junction is also reverse biased, region of operation is cutoff region. Question number 25. The center tap full wave single phase rectifier circuit uses two diodes as shown in the given figure. The RMS voltage across each diode. Answer is option B, 395.3 volt. Given V supply RMS equal to 280 volt. RMS voltage across diode equal to Vm root 2, that is 280 root 2. After solving we get 39.97 volt. Question number 26. A voltage source VAB is 4 sin omega t is applied to the terminals A and B of the circuit shown in the figure. The diodes are assumed to be ideal. The impedance by the circuit across the terminals A and B is. Answer is option B, 10K. During positive half cycle, D1 is forward biased and D2 is reverse biased. Now the circuit becomes like this. Therefore, the impedance equal to 10K. During the negative half cycle, D1 is reverse biased and D2 is forward biased. Now the circuit becomes like shown here. Therefore, the impedance equal to 10K. Question number 27. In the transistor circuit shown below, the collector to ground voltage is plus 20 volt. The possible condition is. Answer is option B, emitter to ground connection open. For a transistor, the emitter base and a collector current having the following relationship. IE equal to IC plus IB, also IC equal to beta IB. Here taking VB equal to 0.6 voltage. Applying KVL from 10 volt source to emitter ground, we get 10 minus 47K into IB minus 0.6 equal to 0. That is 9.4 equal to 4.7K into IB. Therefore, IB equal to 0.2 milliampere. The collector current will be IC equal to beta IB. That is 0.2 beta milliampere. The collector to ground voltage VC will be calculated by applying KVL from 20 volt VCC. That is 20 minus IC RC. IC into 10K equal to VC. From the equation 1 clearly, VC will be less than 20 voltage. Given VC equal to 20 volt. Case 1. When collector emitter terminal is shorted, VC will be 0 voltage. Case 2. With an open emitter to ground connection, there will be no collector current as the circuit is now open circuit. That is IC equal to 0 milliampere. The voltage at the collector using equation 1 will be 20 volt now. This is a possible situation. That is the answer. Case 3 is the with the 10K resistor open, the 20 volt voltage source will be disconnected from VC. So VC cannot be 20 volt. Case 4. With the collector base short circuited, the collector to ground voltage will be less than 20 voltage from equation number 1. So the possible case is case 2, which is emitter to ground connection is open. Question number 28. Current I for the circuit shown will be, answer is option A, 3 milliampere. Vp equal to minus 18 volt, Vn equal to 0 volt, Vp minus Vn equal to minus 18 volt. So Zener diode will work in breakdown region. It will act as a constant voltage source. Vp equal to 24.2 volt, Ve equal to Vb minus 0.7. 24.2 minus 0.7 equal to 23.5 volt. I equal to IC equal to IE approximately equal to 23.5 minus 18 divided by 1.8K. That is 3.05 milliampere is the correct answer. Question number 29. RC network shown in the given figure can provide maximum theoretical phase shift of. Answer is option C, 270 degrees Celsius. The given circuit consists of three RC networks connected in cascade. In a passive RC network, where the input is connected to a capacitor and the output voltage is taken across a resistor, then the circuit is known as high-pass RC circuit. It is given here. The corresponding frequency domain analysis can be done by the circuit. By voltage division rule, the output voltage V0 of j omega equal to Vi of j omega into R divided by R plus 1 by j omega. That is Vi of j omega into RC j omega divided by 1 plus RC j omega. Therefore, V0 divided by Vi equal to RC j omega divided by 1 plus RC j omega. Put S equal to j omega. We get V0 by Vi equal to RCS divided by 1 plus RCS. Phase shift of above equation is 90 degree minus tan inverse of RCS. A single high pass RC circuit provides a phase shift of less than 90 degree at a non-zero frequency. For maximum theoretical phase shift, put R equal to 0 in equation 1, we get angle phi equal to 90 degree. Hence, for the three RC high pass networks connected in cascade, the total phase shift is 90 degree into 3, that is 270 degree. Question number 30. A circuit using op-amp shown below as voltage shunt feedback is the correct answer. Identification of feedback topology. Identify the feedback network or element is the first step. Second step, if all the output side feedback is connected to the output of the circuit directly, name it as voltage sampling or else current sampling. Step 3. If all the input side feedback is connected to the input given to the circuit directly, name it as shunt mixing or else series mixing. Here, feedback element is both R1 resistors. Step 2. The feedback element is directly connected to output, so voltage sampling. And step 3. The feedback element is directly connected to input, so shunt mixing. Hence, the circuit is voltage shunt feedback. Question number 31. The Boolean expression of the output of the logic circuit shown in the figure is, answer is option B, Y equal to A bar B bar plus AB plus C bar. The output of XOR gate is X equal to A B bar plus A bar B bar A bar B. The output of NAND gate is XC C whole bar, where substitute the value of X, which is equal to A B bar plus A bar B into C whole bar. Apply the De Morgan's law, that is A B bar plus A bar B whole bar plus C bar. We know that A B bar plus A bar B whole bar is the simplified form of X NOR gate, that is A B plus A bar B bar, and finally C bar. C bar is there, A B plus A bar B plus C bar. In a sequential circuit, the outputs at any instant of time depends on, answer is option B, on past output as well as present input. Sequential circuits produce output based on the current input and previous output. That is, sequential circuit include memory elements that are capable of storing binary information. This is the block diagram. Sequential circuit is a combinational circuit with memory element. Difference between combinational circuit and sequential circuit. Combinational circuit, its output is determined by the present value of its input only. Sequential circuit, its output is determined by the present input as well as past output values. Combinational circuit, it does not have a memory and a feedback path from output to input. Sequential circuit, it has a memory element and a feedback path from output to input. Combinational circuit is simpler. Sequential circuit is complex. Example of combinational circuit is adder, subtractor, demux, multiplexer, decoder, etc. Example of sequential circuit is flip-flopper, counter, shift registers. Question number 33. How many flip-flops are required to build a binary counter circuit to count from 0 to 1, 0, 2, 3? Sequential circuits produce output based on the current input and previous output. Here is the flip-flop. Given n equal to number of count equal to 1, 0, 2, 3, and small n is the number of flip-flops. Counters is a sequential logic circuit that has a clock input signal and a group of output signals. It represents an integer count value. Internally, counters use flip-flops to represent the current count and to retain the counts between clocks. n values can be counted with n number of flip-flops. Its relation is 2 raised to n greater than or equal to n. Therefore, 2 raised to n greater than or equal to 1, 0, 2, 3. Therefore, the value of small letter n, that is number of flip-flops, is 10. Question number 34. For a flip-flop formed from two NAND gates as shown in the given figure, the unstable state corresponds to, answer is option A, x equal to 0 and y equal to 0. The given figure is a RS flip-flop. A NAND-based flip-flop goes to an unstable state when both the inputs goes high. This unstable condition arises when both the inputs are low. Here the truth table of RS flip-flop. Set a reset output. 1, 1, no change. 0, 1, Q equal to 1. 1, 0, Q equal to 0. 0, 0, invalid state. Can't use it for data storage. The bistable RS flip-flop is activated or set at logic 1 applied to its S input and deactivated or reset by a logic 1 applied to R. The RS flip-flop is said to be in an invalid condition if both the set and reset inputs are deactivated simultaneously. That is when both S equal to R equal to 0. Question number 35. The address bus width of a memory of size 1024 into 8 bit is, answer is option A, 10 bits. The total memory can be calculated from the number of address lines and data lines. That is total memory equal to 2 raised to address lines into data lines. Here 2 raised to address lines equal to 1024. That is number of memory location. Number of data lines equal to 8. Therefore, 1024 equal to 2 raised to 10. Hence, the address bus width is 10 bits. The data bus of 8 bits will be required to read or write data at each 8-bit memory location. Question number 36. The number of comparators in parallel conversion type 8-bit A to D converter is, answer is option C, 255. Flash type ADC. It is also called parallel type ADC. It is the fastest ADC among all the ADC types. An n-bit flash type ADC requires 2 raised to n minus 1 comparators, 2 raised to n resistors and 2 raised to n into n priority encoder. The number of comparators required to build an 8-bit flash ADC is n equal to 2 raised to 8 minus 1. We get n equal to 255. Question number 37. An analog voltage is in the range of 0 to 8 volt is divided in 8 equal intervals for conversion to 3-bit digital output. The maximum condensation error is, answer is option B, 0.5 volt. We know the maximum condensation is QE max equal to delta divided by 2, where delta is the step size, which is equal to V max minus V minimum divided by L, where capital L is the number of levels. Here given N, which is equal to 3. Therefore, the number of levels equal to condensation level L equal to 2 raised to n, we get 8. With analog input range 0 to 8 voltage and condensation level L equal to 8, the step size delta equal to V max minus V minimum divided by L, we get delta equal to 1. Now the condensation error, maximum condensation error is QE maximum equal to delta divided by 2, which is we get answer is 0.5 volt. Question number 38. The frequency deviation produced in a VHF carrier by a signal of 100 Hz is 50 kHz. The frequency modulation index is, answer is option C, 500 radians. In frequency modulation, the modulation index is defined as the ratio of frequency deviation to the modulating frequency. MF equal to delta F divided by FM, where MF is the modulation index, delta F is the frequency deviation, FM is the modulating frequency. Given delta F equal to 50 kHz, FM equal to 100 Hz, MF equal to, after substituting this given values, we get MF equal to 500 radians. Question number 39. In NPN transistor, when emitter junction is forward biased and collector junction is reverse biased, the transistor will operate in, answer is option A, active region. The transistor operate in the active region where the emitter junction is forward biased and the collector is reverse biased in the NPN transistor. For any amplification, that is voltage or current, the transistor should be operated in the active region. Mode emitter based junction biasing, collector, spelling is mistake, collector based junction biasing and application. For cutoff mode, emitter based junction and collector based junction are reverse biased. The application is off switch. Active mode, emitter based junction is forward biased and collector based junction is reverse biased. Application is as amplifier. Reverse active, emitter based junction reverse bias and collector based junction forward bias. Application not much use. Saturation mode, emitter based junction forward bias and collector based junction is also forward bias. On switch. The last question of this part 2 is question number 40. A triac is a semiconductor device which acts as, answer is option C, 3-terminal bidirectional switch. A triac is a bidirectional thyristor with 3 terminals. That is, it can conduct in both directions. Its 2 terminals are usually designated as MT1 anode 1, MT2 anode 2 and the gate by G as in thyristor. When in operation, the triac is equivalent to 2 SCRs connected in anti-parallel. As the triac can conduct in both directions, the terms anode and cathode are not applicable to triac. It is used extensively for the control of power in AC circuits. Thank you.